Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about ocean thermal energy conversion. So let's dive right into it. This is a viewer request, so I'm obliging the request. So what exactly we are talking about when we are talking about ocean thermal energy conversion? Well, we are talking about solar energy that is trapped on the ocean surface because, well, sun is working 24 into 7 into 365. So where the most of the heat is falling onto, it's falling onto the sea because again, it's covering most of the planet Earth and it heats it up because again sun is a very powerful reactor, so it heats it up. Now here's the trick, it does heat it up, but the deeper ocean, basically if you take the upper surface water, that would be around, let's say, 20 to 30 degrees Celsius. Generally it would be 20 25, but let's go with that, let's say 20 degrees Celsius. But what about if you go down deep enough? Let's say you went down, let's say 1 kilometer deep enough. Here's the, at that point you will be getting around 4 or 5 degrees Celsius water. So that's the inherent thing. The surface, there is a like a zone around the equator where you have a lot of hot water on the surface, but in that same place, in that same hot zone, if you go down deep enough, you will have a scenario where you'll have a cold water. So you will have effectively a temperature delta, a high, basically high temperature would be wrong thing, basically warm temperature and cold temperature in the same place. Now here's the interesting part. Wow, that's some lightning. The interesting part about this is basically it's 24 into 7 into 365. No matter what happens, because of the large volume of water we are talking about, because of the ludicrously high thermal mass of water, it inherently does not change. Like again, it will change a little bit in winter, it will go a bit up in summer and all that, but overall, it's nothing. It's like you cannot extract enough energy out of this to have any effect on that. Why? Again, we have to compete against sun, and sun is like, bro, I got this. So that's the reality of it here. It's solar energy we are talking about. So how the heck we get some actual work out of it? That's why the word conversion is in the name. You have to understand that if you want efficiency, the first thing you want is high temperature delta. Basically the difference between your hot side and cold side should be larger. That's why we burn coal at such a ludicrous temperature, like 600 to 800 degrees Celsius. Steams are especially in super critical scenario, we push steam, basically water vapor, to as high as like 1000 degrees Celsius. So reality is you want higher temperature delta. The higher the temperature delta, more awesome you're gonna get. Here we are like opposite of that, you barely have any temperature delta. So to extract energy from this kind of state, we have to utilize low boiling point fluid, basically specifically ammonium and CFC. Now again, CFCs have some variants that are not as destructive to ozone as other variants, but it is something that has been used and could be used if you need to. Ammonia has its pros and cons, so it's not like clean cut just use ammonia, but many architecture do utilize that. Ammonia has low boiling point, basically it will evaporate as low as 20 degrees Celsius, and to make sure that even if in low scenario you get that, you will put it in partial pressure. So you're gonna have an evaporator which will be under partial pressure. It will have a fluid, aka it will have liquid ammonia, and it will boil using normal surface level seawater, which will be around 25 degrees Celsius. So it will boil it off. Because of the low pressure, the boiling temperature has been dropped down even more, so it will boils it up. Now it has thermal energy and kinetic energy that goes to the turbine. Turbine extracts as much kinetic energy as it can, and then it lets it go. Now what, once it lets it go, it's still in vapor phase. It's still, while it has dumped its a lot of its thermal, basically kinetic energy, it has not dumped 100% of it, so it's still in what we call vapor phase. So you have to condense it. We need a condenser. Now here's the interesting part, because we extracted the energy to create that temperature, basically to run the condenser, you go down basically seabed as low as you can go, and you extract cold water from there. And at that point you can extract cold water around 5 degrees Celsius. So your hot side is 25 degrees Celsius, your cold side would be 5 degrees Celsius, and you have temperature delta of 20 degrees Celsius. And because of immense, as in like ludicrously huge thermal mass, you cannot change this temperature. It's not like a geothermal heating and cooling. Basically it's good for small homes. The moment you start to do that with a large building, the soil heats up, it cannot absorb that kind of energy. This puppy is like, bro, I don't care, like you can do whatever you want to do with, like you have to extract gigawatts of it before it even has a 1 whole degree of water drop. So 1 whole degree of temperature drop, so to say. So that's the reality. Basically you take warm water, you take cold water, and warm water is used to boil low boiling temperature. Then you run the turbine runs the generator, you get the power, and you basically condense the vapor back into liquid using the cold side, basically deep sea. Now that's how it works. And here's the deal, depending on depth of the ocean, because if you want 5 degrees Celsius water, it's not easily accessible, like, oh, just, go 1 meter down below or something like that. You have to go fairly deep. So generally it's classified at around 1 kilometer. There you can be like absolutely sure you're gonna get cold water. So if you are in a cliff kind of area, basically if your coastline has a cliff to it, and I mean on the seaside, not on the land side, as in on the seaside where you're like, okay, I barely went into like, 500 meters or something like that, and bam, it goes into a cliff. There people generally built it in offshore platforms itself, where it will be like, it's just pipes. But if let's say you have to go 5-6 kilometer, then you will have basically floating platforms where you will utilize that one, because running pipes for that long would be ludicrously energy wasteful. You will waste all 100% of the energy that you will get. So because you have to be mindful, while their energy present there is huge, the temperature delta is so low that you're not extracting like 100% of it. Barely you are getting 10%, barely. Like theoretical maximum is at 7% with current design. Again, future design could push it to 10. So this is the working of it. Basically everything is happening in less than 20-25 degrees Celsius. So what are the benefits of doing something this convoluted? Well, here's the thing. It's the only power source that you can be like 24 into 7 into 365 base load. Basically, not only it's like, okay, I'm giving you this much hour, go and go YOLO on it. It's also like I can throttle it. Now that throttling part is very important, because if you are familiar with wind turbines, you know for a fact that many times wind turbine had to be shut down, which is lost revenue. Ideally, you do not want to do that. Even in coal power plant, you want it to be like a smooth curve so you can adjust the furnace temperature properly. This puppy can also react to something like that. Basically, if you have to a scenario where it's like, bro, power spike has happening, can you increase the flow? You can, because again, it's all you are talking about is fluid dynamics. You can have throttles, valves, and all that will give you control. Now again, the control won't be like, okay, it's 100 kilowatt. Let's say this plant is 100 kilowatt. You're not gonna expect 200 kilowatt of it. It's just that, let's say during night time, it's like grid is like going in low energy, so you can throttle it down to 50%. That would be really useful. So that removes the need for battery banks. That is a really good thing. It's like you have a generator, that's it, game over. You don't need huge Tesla battery banks or something like that. So that's one awesome thing. These two things alone makes it amazing power source. Then we come to another part. It can be done offshore. While this 100 kilowatt power plant is built on basically seaside, you really don't want to expand land there, because again, land is a valuable commodity. You do not want to just build as much power plant as you want to do. Many times solar farms are dealing with this. Is just solar panel parts are the cheap part. Is that buying that, like, hectares and hectares of land is the expensive part. So many times people are like, dude, okay, that's cool and all that, but again, the plant will become bigger if you want to build a huge plant. So you can directly go offshore. You're like, dude, I'm untethered from the basically land. You'll have complete sea, which is desirable for many scenarios. And it has energy security. So if you're familiar with hydro dam also gives this kind of advantages. But all rivers are changing in their water flows. All of the glaciers are sinking, and at this point in time, it's no longer like, oh, it might dry up in the future. It's like, dude, it will dry up in the future. It's just how many years? 50 years or 75 years? So at this point in time, that does not have the long-term viability where it's like, it's secure, we got this, we don't have to worry about it. No, 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 that's gone. That era is gone. This puppy still brings that era back, and it's like, you have power source, nobody can tamper with it. So if it's that amazing, what are the consequences of this? Well, consequence is ludicrously high capital investment, because you have to take out a huge loan to buy this. That inherently makes your per kilowatt electricity that you are selling more expensive. That is the first problem. Like, if you can't afford it, what's the point of it? It's like, yeah, you watching Lamborghini, but again, you're gonna buy a minivan. So that's the whole thing of it. If you can't afford it, it's pointless. So that itself is a huge wall. That's like there's a giant wall right there. Then you come to another aspect. Like, technically, solar panels are also very expensive. Quality ones are ludicrously expensive. And talking about grid tie inverters, those are also not cheap. However, they are simple equipments. This puppy, not only is more expensive, it's also complex. Basically, you are talking about pipes that should be able to hold basically partial vacuum inside them, while having ammonia renewal, because ammonia is not an inert material. It's not just like, I don't care, like, it will have effects on your metal, so you have to be mindful of that. And then you deal with seawater, which has a tendency of destroying every single thing known to man. Seawater can destroy almost everything. If not outright destroy, it will damage it. So flat out, the complexity is high. The maintenance is on a different level. Basically, solar farms right now, they are classified as maintenance, right? Because all you have is like tiny robots that are like Roombas. Basically, Roombas for solar panel is just going up and down on the string and just cleaning it. That's it, done, game over. Sometimes you will have some breakdown where inverters breaks down, you just have to change it. Done. Simple solution. Here, again, you have so many fluids working together. You have cold fluid, you have hot fluid, you have a working fluid. All these things require, again, maintenance. So your maintenance cost would be high. And then we come to the final part. The lifespan is very short. Why? Seawater. Seawater is not something that hey, I have a heat exchanger and seawater is going through it, and I'm gonna have awesome thermal exchange. That's not gonna happen because sea life has a tendency to grab to almost anything, including metals. So it will create a life form on top of it, and then your thermal efficiency will disappear. And that has been found with all thermal power plants. They're like, dude, this is a very idiotically painful issue. So you have to clean it, regulate, like even in the long-term designs. Basically, if they are designing on a 100 megawatt scale, they have rovers, basically robotic submarines, and they will go down, submergible vehicles, and they're gonna clean the pipes because that's a big enough issue. Again, you have to pay for it. And India also tried to build basically a variant of a basically test plant of around 1 megawatt scale. The deep sea pipe broke. So that's the reality of it. It's very expensive just to get started. Then also it's very complex. It's not something like, hey, this is a panel, just attach like a plus and minus to inverter, go home. It's not like that. It's very complex. Maintenance wise, it requires constant maintenance. And then in terms of lifespan, do not expect it to have lifespan of, let's say, a solar panel compared to like 25 years of lifespan. So even with all those amazing power, like 24 into power, 24 into 7 power supply, it still is not that desirable. Now, what is the future of it? Well, it does have one advantage, that it inherently has enough power that you can power entirety of humanity out of it. And I mean, truly entirety of humanity. You don't have to worry about fusion that is 30 years away. So you don't have to think about that. Let's like extract this much power out of it, because there are systems that are simple enough, something like this, let's say wave power. Problem with that, wave is inherently wind energy. Inherently it's not that energy dense. This puppy is on a different level. It's like, dude, if you extract even 1/10 of a 1%, we don't even have to think about electricity at that point. So it has power, so it has potential of growth. Then it also has grid tie capability, so we no longer have to like, okay, build a giant gravity battery banks, gravity city battery banks, or like giant thermal cells or something like that. You don't have to think about that. That inherently makes it simple. However, the efficiency has to improve because of the low temperature delta. Inherently, it's limited to like a theoretical maximum is classified as around 77%. Why I'm saying 77%, and maximum we achieved in lab condition is around 5%. So we have to exceed that. Like if 6% we achieved, at that point people are saying no, that will be break-even point where you can sell enough electricity to justify the cost. And then we have to figure out to build parts that are immune to biofouling. Basically, things we have learned some with offshore wind farms. We have learned some things with it, so it is doable, but it's not very easy because again, these things just have a mast. Here you have heat exchangers, because even a micron thick layers of basically biological material will drastically compromise your thermal efficiency. So we have lot of work ahead, and not to mention somebody has to make it cheap. But so far, Lockheed Martin is pouring their money into this, and that's a big company. That's a big company with a deep pocket. And I provided a video down below for extra research and all that. So there is a hope in this. Not an easy one, but there is a hope in this. So this was my basically presentation on basically ocean thermal system. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me excellent disappointment. Please leave a comment because I like to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.